Today's CRD-equipped passenger vehicles are designed to offer exceptional performance, good fuel economy, and must meet the highest levels and environmental emission regulations. Their exhaust after-treatment systems must be understood and serviced by proficient service technicians. These vehicles have very complex exhaust emission management systems, which, if not understood, will challenge all automotive service and repair technicians. When a CRD engine is operating, particulate matter or soot from the waste exhaust gases gets trapped in the closed channels of the DPF's porous ceramic core. When this occurs, the vehicle's ECM burns off this particulate matter, clearing the saturated DPF and thus improving vehicle performance and fuel economy. The saturation level of the DPF is calculated by the ECM. If it exceeds a defined threshold limit, the ECM initiates an active regeneration of the DPF by means of additional pre- or post-fuel injection events. These secondary or additional fuel injections generate the heat required to convert or burn off the particulate deposits stored within the ceramic core. Temperatures in excess of 600 degrees Celsius may be reached. The ECM, fuel injectors, exhaust gas temperature sensors, and differential pressure sensors are responsible for the control and monitoring of the active regeneration process. The main component of this vital emission management control system is the ECM. This device has critical vehicle performance and emission control data parameters, or MAPs, stored in the ECM's memory. This data cannot be modified and is only accessible via the vehicle's DLC connector using a suitable diagnostic scan tool. Diagnostic trouble codes, or DTCs, will be stored if any emission faults occur as a result of the conditions falling outside defined thresholds. Depending on the severity of the fault, the vehicle may enter a reduced power mode. An exhaust gas recirculation, or EGR valve, is a component that has been designed and utilised as a nitrous oxide or NOx reduction device. Because NOx is a byproduct of high combustion temperatures, the EGR's main role is to keep these temperatures to a minimum level. The EGR valve allows a portion of spent exhaust gases to return to the combustion chamber during the intake stroke. The volume taken up by these spent gases reduces the available space for a fresh air charge. With less oxygen in the combustion process, there is less heat generated, so NOx emissions are effectively reduced. Exhaust gas recirculation devices on CRD passenger vehicles are controlled by the ECM. They must work within the DPF regeneration programming guidelines, as they are both designed to achieve opposing goals. It'd be a pointless exercise operating the EGR valve lowering combustion temperatures when the DPF requires an increase to perform a regeneration event. Oxygen, or O2 sensors, were traditionally fitted to a petrol fuel vehicle's exhaust system. Originally located before the catalytic converter, all new petrol fuel vehicles have a pre- and post-O2 sensor fitted. These are feedback devices for the ECM to determine if the post-combustion mixtures are within predetermined levels. CRD passenger vehicles are now using the same type of feedback devices for engine management and emission monitoring. Rich combustion mixtures result in excess diesel particulate formation. The O2, or air-fuel ratio sensor as it's also known, is mounted in the exhaust manifold close to the exhaust ports. These type of sensors use wideband or Nernst cell technology and are very effective at identifying the fuel-air mixture values. A differential pressure sensor is mounted across the DPF and provides feedback to the ECM on exhaust pressure difference. These pressure values are used to help calculate the soot level percentage of the DPF. This sensor input signal is vital for the ECM to command a filter regeneration cycle to remove the soot deposits from the DPF assembly. The differential pressure sensor is connected to the DPF via metal pipes. This sensor accurately measures the pressure at the entry and exit of the DPF assembly, and the signal is sent to the ECM. Some manufacturers choose to fit only one DPF pressure outlet port. This is usually towards the front of the assembly. This value is compared with atmospheric levels to obtain the DPF pressure drop. An exhaust gas temperature sensor is very similar to a coolant temp sensor in design and function. The ECM is able to determine the exhaust gas temperatures via return voltage values. Most new model vehicles are fitted with two exhaust gas temperature sensors. One is mounted in the exhaust manifold close to the exhaust ports, and the other is mounted in the DPF assembly. The ECM uses feedback from the EGT sensors to maintain positive control over the various DPF regeneration cycles. Some light-duty diesel manufacturers use a fuel vaporizer injector that is mounted on the exhaust immediately before the DPF assembly. This is an older type system that has predated CRD control. When the ECM commands a regeneration cycle, this injector supplies heated, vaporised fuel directly into the vehicle's DPF. This system negates the requirement of the vehicle's engine fuel injectors to perform post-fuel injection pulses. Under normal driving conditions, the engine doesn't generate enough heat to oxidise the soot stored in the DPF. This process requires exhaust temperatures above 550 degrees Celsius. The ECM commands additional injection pulses, known as post-injection, that results in more heat generated within the combustion gases and DPF assembly. The process is known as regeneration. Passive regeneration occurs naturally, without any intervention by the ECM. This type of DPF regeneration occurs in a CRD vehicle often without the driver being aware or feeling any change in the vehicle's performance. On most CRD vehicles, there is no dash warning light that indicates this type of regeneration is taking place. Under certain driving conditions, a high percentage of nitrogen dioxide is produced by an oxidising catalyst mounted before the DPF. When exhaust temperatures of around 250 degrees Celsius are reached, the nitrogen dioxide combusts with the carbon or soot particles trapped within the DPF substrate. These lower exhaust temperatures are generally reached by most CRD vehicles under highway or increased load operating conditions. The ECM is able to monitor the progress of the passive regeneration using inputs from the exhaust gas temperature sensors and DPF pressure sensors. A calculated DPF soot accumulation level, measured as a percentage or in grams, is recorded by the ECM and is referenced to determine if the passive regeneration event is successful in reducing the soot mass. To maintain the necessary temperature within the DPF for passive regeneration to occur, different ECM control operations may be performed. The ECM may alter the intake air valve angle. It may perform minor post-injections or even alter the turbocharger boost pressure. These operations all serve to maintain the exhaust gas temperature within limits, while keeping the vehicle's fuel consumption as low as possible. If the vehicle's drive cycle history indicates more frequent city, stop-start and short trip events, the DPF will accumulate higher levels of carbon deposits. The ECM counteracts this state by performing an active regeneration event. An active regeneration uses oxygen to react with the carbon molecules trapped within the DPF substrate, rather than nitrogen dioxide. The oxygen reacts with the trapped carbon at temperatures of around 600 degrees Celsius. The increased exhaust temperature and oxygen reaction is more efficient at burning off the soot deposits to carbon dioxide. Secondary injections will be initiated by the ECM to raise the temperature in the DPF to these higher levels. The conditions required for an active regeneration event to begin may include the DPF saturation threshold, the coolant temperature, engine speed and load conditions must all be over a predetermined level. If any of these conditions are not met due to frequent short journeys or multiple regeneration interruptions, the DPF warning indicator will flash, informing the vehicle operator that a specific drive cycle is required until the regeneration process has been completed. If the regeneration drive cycle is not performed correctly, the check engine warning light will also illuminate and a DTC will be logged in the ECM. In this event, a forced service regeneration must be carried out by a proficient automotive repairer. A forced regeneration is performed by a service technician using a manufacturer's specific or aftermarket diagnostic scan tool. Caution must be taken when executing a forced regeneration, as the extreme exhaust gas temperatures can cause ignition of oil and grease spills on the shop floor. It must be carried out in a well-ventilated area due to the quantity of particulate matter being converted to CO2. Do not initiate the forced regeneration if there are any DTCs relating to other engine system faults. Any non-related DTCs must be rectified first, or irreversible damage to the DPF may occur. Unfortunately, regeneration events do not remove all of the stored particulate matter. Over time, a residue layer forms over the ceramic substrate core that resists the ECM's attempts at removal. Eventually, the DPF will need replacing. A DPF has a limited lifespan. However, this may be dramatically reduced when factoring the customer's driving profile, mechanical failures, substrate contamination due to coolant, oil, or poor fuel quality, and the number of active and forced regenerations. Best practice dictates that a DPF should not be removed and cleaned. In the event of excessive soot accumulation and permanent blockage, it must be replaced. In effect, the DPF is a filter. It will eventually become blocked and need to be replaced. The engine oil life in CRD passenger vehicles is reduced during DPF regenerations. Excess diesel fuel mixes with the engine oil due to the additional injection events. It might be necessary to change the oil more often if frequent regeneration events are occurring. CRD vehicles fitted with DPFs require the use of low ash engine oil. When replacing or topping engine oil, only low ash oil complying with the viscosity and specifications stated in the owner's manual must be used. If normal engine oil is used instead, ash, which is denser than soot, will accumulate in the DPF, which in turn reduces the amount of soot the DPF can store. Ash in the DPF cannot be burnt off and can severely reduce the life of the DPF assembly. So now we have a reasonable understanding of a diesel engine's exhaust emission control system, its operation, and the 3 DPF regeneration cycles used. Diesel emission control is complex, yet necessary in today's world. Thanks for watching.